Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over the amine reactions. Now this is section 5, and section 5 is about most of the amine reactions, but section 6 goes into a little bit more. It's actually, section 6 is called the arene diazonium reactions, and it's because amines become diazonium groups, and that has a whole series of things to learn about that warrants its own video. Okay, so this is most of the reactions, but one topic short, which is the diazonium groups. Now, as you'll see here in this video, most of these reactions here, almost every one of these, except for the last two, are reactions that you already know, or you learned, or you were supposed to learn from the past. Okay, but we're going to go over it carefully just to refresh our memory on all these details. Okay, it's very important that we do that. But like I said, there's really nothing new except when we get to the last two, Rothman and Cope. All right, let's go ahead and start up by doing the first one. Now, alkylation is actually something we discussed in the preparation of amines. So it's really, this is very quick. If you have RBr, you can treat it with the nitrogen, let's say NH3, and this would make an amine, right? But it's also an amine reaction because this nitrogen, once it reacts, it could become a monoalkylated amine. It'll keep going on, right? So it really is a reaction of its own. So this right here will come in, SN2. It'll come in and push out the Br, and we'll get an RNH3 plus, and then we'll eventually pull off the H. We could use an NH3 or a Br minus, something to pull off that H. Or if we don't care what's doing it, we could just write minus H plus. And now we have an RNH2. So this is SN2. R equals methyl, primary, secondary, allyl, or benzyl, right? So those are the things that it could be in order for this to go through an SN2 reaction. And that's really it. I mean, there's not much to say here. We do know about polyalkylation, but since we already talked about it, it's not much to really mention here at all. So I'm just going to move on, because this was, and the reason why I keep saying that, if you didn't watch in the right order, I taught you this reaction is the very first thing in section 4, right? This is the first reaction we discussed, the alkylation of an amine. And so, that's why I'm just going to stop here. Okay, the next thing we could talk about is acylation. And now this is chapter 17. This is chapter 17 reaction. And so what we discussed back then, and this is very important that you can bring this back in memory now, is that you can take, let's say an acyl chloride or an acid anhydride. I'll do one at a time. If you treat this with an amine, let's say ethyl amine, but it could be any amine, right? So it could be primary or secondary. Now it can't be tertiary. And the reason why, so this could be a primary amine, secondary, or ammonia. These are the things that nitrogen can be. Okay, now the reason why it can't be tertiary, which I'll kind of show you right now, if this nitrogen was to come in, and this opens up, then we get an O minus, we have a Cl, and we have a NH2 plus, right? Like that. Well, remember that with Cl, it's such a good leaving group that this is going to close down and the Cl is going to leave. And so we're going to wind up getting an amine that's positive right now, right? So we'll go like that. Plus we get Cl minus. Now we have to remember, and this is important, I have to say, because there are some times, some years that you'll see where they actually tested students on this concept and people weren't prepared for it. So let me just kind of go on a little bit further. So this right here is going to pull off the H and you're going to make it neutral. Now back when we did this chapter 17 theory, what we said was that there's a very special characteristic that you have to remember about amines. Well, when you do this acylation, we add the acyl group onto a nitrogen. We make it an amide, right? This is just an amide. But what we had to remember is that whenever HCl forms, we had that side reaction, remember that? Where HCl will now react with a nitrogen that didn't react yet, and it'll turn it into an ammonium ion, NH3 plus and Cl minus. So this was a side reaction that we were very sensitive to remember. We said we had to remember this. And I'll tell you how this came up on an exam. So one year, I think it was Professor Lauer but I'm not 100%. One, it could have been, I think it was lower. One year, he gave a question of this with that, something like this. And students knew to make an amide. But he had you do a separation technique, and no one understood really how to begin, because what you knew about was you made an amide, but what else did you make? So people forgot, because back in chapter 17 you learn about this, and when you get to chapter 20 you're not really thinking about this detail. But you have to remember that not only do you make an amide, but you also make this right here. And so when you have this formation, you had to be sensitive to this formation here, and this would go into the aqueous layer, right? So that's kind of a trick that he had proposed, and if you didn't catch it, you lost all your points for a separation. So let me be clear. When an amide is formed with acyl chloride, we also are going to make this side reaction. So every time an HCl forms, we then use that HCl to protonate an amine that did not react yet. So do you remember how we got around this problem? We said that if this amine is going to be eaten up, so for every one time it does this, another time it does that. So for every 2 amines, you get 1 amide, right? Think about it. For every one time you make an amide, you're using up 2 amines. So what we said is the trick is to use excess. If we have excess, so if we wrote excess here, then it wouldn't matter, because let's say there's a million of these, there's 2 million of these. So you will get a million of these formed, which is all you can get, right? Because if this is the limiting reagent here, this is the one that is going to run out. So if we have a million, no matter how many of these you have, you can only make a million amides, right? So that's the idea. We kind of put the focus on this, and we didn't have to worry so much about this forming down below. All right, so I just want you to be sensitive to this, because on this exam, if they happen to bring up a separation reaction, right, and somehow you see like let's say, for example, it says this right here with NH3 becomes A, B, and then how do you separate them out from each other, right? So think about it. Well, A is going to be an amide, B is going to be an NH4Cl, right? And the NH4Cl is positive and negative, so in the aqueous you're going to have NH4 plus Cl minus, and then the amide will be in the ether, right? It's not positive. And then if you just use a base, like let's say a strong base, let's say actually let's just use well, for this let's just use even hydroxide, okay? So we use a base, then now in the ether layer you're going to have NH3, and then in the aqueous layer you'll have, let's say, sodium hydroxide. So you have sodium and Cl minus. So you see how we did that? So we had to realize that by reacting these two together, you get this, and then you see how it goes around. So this is the ether layer right here, right? So I hope this is clear. This is kind of showing you how, kind of like a problem that came up as an example. Okay. So now the next thing I want to talk about is that there are other variations to this concept. So another one that we could do, an alternative, is if we use an acid anhydride. So acid anhydride with an ethylamine, same thing. We would need excess, and I'll show you why. This nitrogen is going to come in. It's going to open up. Now, it doesn't matter which side it attacks on the anhydride. We'll worry about that for the final, but for now, it's not going to be about the anhydride. So it should be symmetrical on this exam. For the final, we'll come back into which is more positive, which is more likely to be attacked, but not now. Okay, so there it is. And now from here, this closes down, and we want to throw this out, right? So now we have this right here, and hopefully none of this is new. This is all stuff that you're familiar with. So this is positive. So then from here, you could just have the O pull off that H, and we get to the end, right? So we have an amide formed, plus we have a carboxylic acid. Now the thing about it is that when you have this anhydride, and this kind of came up on your exam, but it came up in a ring system, when you make carboxylic acid, the thing that you have to keep in mind is that as soon as it's formed, it's going to protonate an amine that didn't react yet, right? So we're going to wind up having, again, a side reaction where this carboxylic acid here will react with an amine, and you'll wind up getting carboxylate plus NH3 ethyl positive, and those two will hang on together, right? So this is a side reaction again that would happen, and you can't control that from not happening. So this was actually a reason why you're not going to get both sides of the anhydride to become an amide. It won't happen because this right